Hi and welcome back. So I think this is going to be the last video of this mini series inside the series of videos. In this mini series, we've been taking a look at what plain like forward neural networks are, how they are progress data information through the network, also how they are going to be trained by an iterative updating process of parameters, which is called gradient descent. Also, we've been taking a look in the last video how you would estimate a neural network for a what is called regression task. The regression task was a task where your target variable is basically a real valued number. And now in this video, we are going to take a look about the small modifications in comparison to the regression task that we need to make if our target variable is now a categorical variable with two or more categories. When it comes to the training of those models, usually one kind of separates between the scenario where we have a binary target variable, that means a yes or no variable, or if the target variable has more than two categories. First, let's take a look at the binary scenario and afterwards at the what I call multi-class classification task. All right, so for the classification task with the binary variable, we have usually the target variable encoded into 0 and 1. Maybe sometimes, people refer to 1 as the category of interest. So assume for a moment you would like to predict, you're working in a bank and you want to predict a default model. So 1 would be, for instance, then if a customer has not been able to pay back its loan and has been defaulting. I think in the area of life science, it's like illness. Usually, people has a certain condition. So I would say mostly, but this is not something you can also define it perfectly the other way around. Okay. Here again, we are just creating a simple example of data. So here it's visualized. We are using two feature variables, x1 and x2. And visually here you can see that especially for larger x1 and slightly smaller x2 realizations, we are looking at class 1 or category 1. And if x1 in tendency is smaller and x2 is higher, we are more likely observing what is going to be class or category 0. And as we also can see, there's a certain overlap, so there's no perfect deterministic relationship here. However, we now would like to train a neural network which at least understands this relationship, that it understands that in tendency, if x1 is larger and x2 is smaller, it is more likely that we have a target variable whose actual category is of category 1. All right, in comparison before, what is exactly the same thing is the data preprocessing. So here we split the data. Also, we normalize the data, again here with the min-maximum normalization, so x1, x2, here originally somewhere between let's say minus 30 and plus 30 overall, or minus 20 and plus 30, both variables. Now after the normalization, x1 and x2 are all bound within the range between -1 and 1. And we split the data into training and test data here. And we are going now to take a look at always sampling 32 observations at each time when we do a gradient iteration step. So like two things need to be adjusted here. First of all, obviously the prediction itself, right? Because before, when we have a real valued number, what we basically did, we returned, the neural network has been defined that it returns a real valued number. But now if you want to make the prediction for a variable that is either 0 or 1, that doesn't seem to work anymore, right? Because what do you do with a prediction of 5 or 7? So this is why what you usually do is you transform the prediction of the neural network from before. Okay, so and the transformation can be seen here. This is how it's done for a binary classification task. So that means, like from before, we have seen that the neural network has been for every observation returning some real valued number. And if you want to, you can picture this real valued number in this scenario here as a score. And the score is going to be higher if it is more likely that this is category 1, and it's becoming smaller and smaller and negative usually if it is more likely that this is category 0. And to directly transform the prediction of the neural network into a value range which makes more sense for a 0 and 1 encoded target variable, it is often converted like this. So this is called the sigmoid transformation. And what it makes sure is that you have in the beginning a score, an output of a regression model, which can be any real valued number. After you put that through, so set would be here like the output for the observation, like the real valued number. And if you go through this transformation here, you will have a number that is between 0 and 1. And in this context, this is interpreted as a probability for being the category of interest. So for instance, for the probability that given x1 and x2 information, how likely is it that this observation is of category 1 and not of category 0, okay? So, and why does it make sense here? Because probabilities, they are defined, they need to be higher than 0, need to be smaller than 1, or equal to 0 and 1. And like if we have something like we have here, so-called disjoint events, so it can be either category 0 or category 1, it cannot be both. Then also the both probabilities for what can happen need to be summed up to 1 again. And this is perfectly met if we would do it like this and if we treat it like this. So, and this is where it is differently handled in comparison to a multi-class classification task, because if you only have two things that can happen, the probability for the one also indirectly defines the probability for the other event. So this is why usually here we still only need one output out of the neural network. First of all, the real valued number, which is then transformed by this transformation to a probability. So the immediate and the direct output of the neural network will be the probability that this is category 1. However, for instance, let's assume this is 60%. Then the probability for that this is category 0 is just 1 minus the probability for being category 1. So it would be then 40% here. So this is why for a binary classification task, your neural network still only needs an output dimensionality of 1 for every observation. So one number for every observation. And as you'll see later, it kind of depends how the loss function is defined. In PyTorch, usually you work with directly the logits. So that means the network still creates a prediction for every observation that is a real valued number. And then when you calculate the loss function that we're going to take a look here, internally the real valued number is first transformed to the probability and then used for calculating the loss. And if you would like, for instance, for a trained neural network, you would like to have those probability predictions to see them for yourselves, you still take the output of the regression model and then apply this function. And then what you then see is interpreted as the probability for being category 1. Okay, so that's like the first modification here. And the second one is now, how can we evaluate if our model is making good predictions? For the regression task, it has been, of course, like the closer the real valued number that we output for every observation is to the actual observation, the better. So this is what the squared deviation is basically capturing here. However, in this context, we need to adjust this. And the way how we adjust this is that we use basically this loss function here that you can see here for every data point, for every observation. And so what this does here is, so y would be either 1 or 0, and y hat is here the probability prediction. Okay, so that means g of z, basically. Okay, so that means if we have an observation that in reality is of category 1, then we have here minus 1 times log of the probability prediction for that category. And then minus 1, so that's becoming 0, 0 sometimes times something is still 0. So if in reality we observe in our data sample a category 1, right? So if the target variable is category 1, then we calculate the loss function value just by calculating minus log of the probability prediction that this observation is category 1. And if we in reality we have category 0, then we have here minus 0 times something, so the first part vanishes. And 1 minus 0 is still 1, so we have minus 1 times log of 1 minus the probability prediction. Okay, so that means those are the two scenarios. So it kind of depends if we have an observation in the data sample, which in reality is category 1, then we calculate the loss as minus log of the probability prediction that this is category 1. If we have category 0, then we calculate minus log of 1 minus y hat. And now what is this? This is again minus log of the probability prediction that this is category 0. Okay, so basically what is used as a loss function for every data point is minus log of the probability prediction for the category that we actually observe here, right? And if you now take a look at the form of this minus log function, it kind of makes sense intuitively, because assume for a moment we're looking at an observation which is in reality category 1, and we have already a very good probability prediction for it. That means it is category 1, and let's say we are here. The model predicts with a 90% probability that it is category 1. Then we have a small number in comparison to what, assume for a moment, your model is currently on a bad track, and it predicts that we're only with 10% probability this is category 1, while in reality it is category 1. Then you would get here a higher loss value. Okay, so intuitively, and this is, I think, in my opinion here, the most important aspect, you will have now always a model which kind of makes a probability prediction, and you take a look, okay, what is the category in reality for this observation, and how high is the probability prediction for that category. And if you have a high probability prediction for the category that you actually observe in reality, then your model is doing something good and your loss value is small. And it's the other way around if the probability prediction is small for the actual category that we observe, because of course a model that kind of understands the relationship here and gives you good predictions here in that context gives you high probabilities for the categories that you actually observe, right? So I hope that this makes sense if one just hears it like this, and if you get like this kind of explanation. But basically that is it. Okay, so that means, and as I said before, that the only thing maybe currently hard to tackle in your mind is, okay, where do I do this? And this is kind of, I would say, special for the way how PyTorch usually does this, because you can include this transformation either when calculating the loss, only when it's about the training, or you can first make the probability predictions and then adjust the calculation of the loss function accordingly. But for PyTorch, it is usually still the definition here as before. So the model, if we define it here, so let's execute this and then I can show you. So sample data, pre-processed data. Okay, that's something we don't need to execute here. This already would completely train a model. But for instance, here for one epoch here, this is how still the output looks like. Okay, so as you can see, those are any numbers. So those would be the predictions of the neural network. But the loss function that we use here is the binary cross entropy loss with logits. And if we quickly take a look at this, I hope we end up here quickly. No, it's wrong. You will see that, or if you read through this here, you will read that it internally then takes these real value number that we have seen here. Okay, one more time, the output of the model. It takes those numbers, then internally the loss function does this sigmoid activation here. So that's like the xn is what we're looking at. And if you give that to the loss function, it first creates the probability predictions out of them and then calculates the loss as we explained in the past minutes. So this is why still if you train it with PyTorch using this loss function, first of all, the neural network definition is exactly the same here. It still creates real valued numbers, but in that context, you can interpret the outcome of this model already here as a score, which is higher, the higher the probability for being category 1. And except for those things like the whole training process, the idea behind the gradient update and so on is all exactly the same as before. Okay, so this is why we're not going to talk about this in detail. And if we do this here, you can see you can track the loss, the training and test loss looks quite okay, even though it seems to overfit maybe a little in the end here because the training loss is smaller than the test loss. Then once you fitted it, now of course, let's execute this here. Your model would still create the scores as before, okay? And with those scores, we cannot directly work because now we still, even if we trained the model, if we need to make the concrete predictions, we want to we now need to make the prediction, okay, is this 1 or is this 0, right? And still we get here the scores. So what we can do is we can, for instance, let me show you how this would look like. I think that should be doing the job here. So starting from the scores of a trained model, if you put this through this sigmoid function, you will now see, okay, those would be probability predictions. So for instance, that means with 85% probability, that is category 1. This here, for instance, is only with 35% probability, this is category 1, which means at the same time around with a probability of 65%, this is category 0. But still, if we have ones and zeros, so in reality, you need to decide, okay, do I think this customer is going to default or not? Then you're still very flexible in what you're doing, but the most common approach here would say is, for instance, you take a look, okay, are those numbers larger or smaller? Okay, sorry, we need to do this. For instance, is like every number smaller or... Okay, wait, if you do it like this, then we can do it. Yeah. Like, is it higher, for instance, than 0.5? And let's also transform this to a number. So that means you take a look, okay, is the probability larger than 0.5? Yes. Okay, then I say, finally, this is category 1. And if it's not, then this is category 0. Okay, but the 0.5 is something you could also play around with. If your model gets better, like for the average task that you need, if you do it like this, it's also okay. But I would say like the naive approach would say, okay, if the probability is larger than 50%, then it's that the corresponding category of interest here, right? Okay, and then finally, to evaluate a model like this, many people may tend to look at the accuracy, which is kind of the intuitive measure of performances or accuracy in terms of what is the fraction of correct predictions. Okay, so correct prediction is either I predict 1 and it is 1, or I predict 0 and it is 0. However, in my opinion, it is more important to take a look at the different errors that you can make when you take a look at the evaluation of classification tasks. So here what we always, so we have true positives and true negatives. Okay, so with positives in this context, one refers to the category of interest. So if it is 1, so if I predict this to be category 1, and in reality it is category 1, this is called a true positive. If I predict this to be category 0, and in reality it is category 0, then this is a true negative. So you can make two errors. You can make the prediction that this is category 1, but in reality it is 0. That would be then the false positive. And you can make the prediction that this is category 0, but it is in reality it is as category 1. That is then the false negative. And if you would like to visualize this, this is a heat map of what is called a confusion matrix. Here on the diagonal, there are the true positives and the true negatives. So basically where you're doing everything correctly, right? So here it is the prediction. Prediction is 1 and actual realization is 1. Those are the true positives. Those are the true negatives. And then here you have the errors, right? So you can see you're making the false negative, right? So you predict 0 and you get 1. And here you're doing the false positive. You predict 1, but you actually it is 0. And I think this is important to look at because here it's not the case, but if you may sometimes identify large asymmetries here, so that your model is struggling with one different type of prediction or one different type of category the most. And this is what you would get revealed when you look at it like this, and what you always will ignore when you're just taking a look at the accuracies. And if you want to quantify this into numbers, you can calculate the precision and the recall. Take a look for yourself, or let's take a look together. So very quickly, for instance, the sklearn package, I think, has it written somewhere. The precision score. And for instance, the precision takes a look at the true positives divided by the true positives and the false positives. Okay, this is the number of. So the precision is intuitively the ability of the classifier not to label as positive a sample that is negative. Needs some time to think about, usually a little bit. And then the recall score is again the true positives, but now in relation to true positives plus false negatives. And that is intuitively the ability of the classifier to find all the positive samples that are of the category positive here. And you can also then quantify, basically you see that here in the heat map if one struggles with like one of those different things here. And also you can calculate this. So if we do that here, I would say this is like taking only a look at the accuracies. Usually maybe it's not enough. Here it's as a simple and simulated example with where everything works more or less the same. It's okay if you because there are no asymmetries here or something like this, but in reality they often are, right? So that is why I would always take a look at this like this. All right, then I think we can still include also the multi-class classification task, because more or less it's just only one thing that is different now here. So now we have more than 2 categories, and this is finally where the dimension of the output of the neural network is usually then exactly the number of categories that we have. So here, if we have 3 categories, then now we are going to define a neural network which generates 3 numbers for every observation in the data set. And again, in the beginning, every output or like every number is again can be interpreted as a score. Okay, so let me take a look if I can show you here. So in that case, so here we have 3 categories. This is why I set the output dimension to 3. And if we would take a look, so this is how the model would make predictions. So for instance, in that case, this is a very negative number, and this is the score which corresponds to the first category. So if we have here category 0, 1, and 2, then if we have a very small negative number here, that means that it is very unlikely that this is category 0. And you can see the scores for category 1 and category 2, they are more or less comparable or like at a similar level with the second one here, or like with the category 2 being a larger. So that means this, with respect to the score, the higher the score, the more likely it is that it is that exact category. Okay, so this corresponds to score for category 0, 1, and 2. And to have the scores again interpreted into probabilities, one often converts them with the softmax function. So without digging too deep here, what that basically does, it converts those numbers into numbers that are between 0 and 1 and that sum up to 1. So again, it is the probability predictions. So here we have 3 events. That means the probability over all 3 possible categories needs to sum up to 1. Every value needs to be equal to or larger than 0, and every value needs to be equal to or smaller than 1. And this is what the softmax transformation does. Still, what you always will get when you do it, you will get the probability prediction that this observation is that specific category. Okay, so maybe let me show you directly how that looks like for the probabilities. So for instance, it would look something like this here. So for instance here, that means e to the power of minus 10, so almost 0. But here we have a 0.10 probability that this is category 1, and almost 0 or 89 or 0.9% that this is category 2. And this is how it looks like once it has been transformed to the softmax function. And when it comes to the training, it works exactly as for the binary classification task. So that means, for instance, if that here, I don't know, maybe we can take a look. So in reality, let me quickly check. In reality, this is category 2 here. Okay, so if that's category 2, then if you would calculate the loss during training, you would take a look at this number. So what is the probability prediction for the category that we actually observe for this observation here? And you want this probability to become large. That means if currently during training this probability is small, the loss value will be higher. And again, it's always the same logic. That means we take a look in which direction do we need to change the parameters of the model such that this probability prediction is increases for the next time here, right? Because assume at the moment it would be not 90%, it would be 10%. Then we take a look during training, okay, actually this is that category and currently the probability prediction is only 10%. That's supposed to give you a high loss value. And with that information, the gradient will tell you in which direction you need to change the parameters of the model to increase this probability prediction. Okay, so that's always more or less the same logic. It always works exactly the same thing. Only minor modifications need to be done for that specific and different tasks that we're taking a look here. Okay, and then maybe let me just also erase this here. The only thing also, which is, so it's, as I said, really the same thing. So the only thing, we now use the cross entropy loss function, but it does exactly the same thing. You can look it up for PyTorch. It's just the automatic handling with the target variable having now more categories that is different here. And besides that, it's all the same. Training is the same. And even evaluation, confusion metrics can be used also. If you're using now accuracies and predictions and recalls, it gets maybe a little, you can become more detailed about it, because obviously you can, for instance, calculate the recall and precision for every category itself, right? So when, for instance, if you take a look at the recall definition, so true positive, in that case would mean, okay, if this is category 2, so the number of true correctly predictions for category 2, and then divided by this number plus every time when we predicted 0 or 1. And we can do the same thing for category 1 and category 0. So that is why you can calculate the precision and the recall for every category specifically. Okay, but this is really very detailed and already is more headed towards how should we evaluate models. And this introduction should be more about how in general, what's the process, what's a neural network, what's the idea, how is it trained. And here are some examples, such to give you some, that you can see how this is done. Also that you observe certain similarities. So here the similarities are always the same sort of pre-processing of the data, the training of the data, and its logic is exactly the same thing. The tracking, the also to this little extent how the evolution of the loss function looks like has been always very similar. And then the differences are, okay, if we switch from regression models to classification tasks, basically what we adjust is the way how the model predicts and or how the loss is calculated. And the difference between the binary and the multi-class classification task is that usually for the binary classification task, the output dimensionality is still 1. And if we then have more than 2 categories, the output dimension of the prediction model is usually exactly the amount of categories that you observe in your dataset for the target variable. All right, so this is still within the series of text modeling, even though obviously neural networks is a very general thing. And hopefully in the next videos it's becoming more clear why I still think it is reasonable to understand what neural networks are and how they are trained when we talk about some text models that we are looking now in the next videos, because they are more or less exactly the same thing. They are neural networks with slightly different architectures, but they have parameters, and the way they are trained is also usually gradient descent based. And more or less, at least for the next text models we're going to take a look at, they are trained by solving multi-class classification tasks. And this is why I think where it relates to the general understanding of neural networks and the typical tasks that we have here in the supervised learning context. All right, then hopefully see you in the next video. Take care and goodbye.